Hello, this is Eric Carden with Harley Chappelle, and this is our capstone presentation on Wildlife Crossing AI, WCAI for short. These are our clients. Our clients are Professor Bernie Boscow, a computer science professor here at SOU, who acts as our liaison to Karen Mager, a professor of biological science with concentration in wildlife biology and conservation, who is also at SOU. Karen Mager is also the client who proposed the capstone project, while Bernie Boscow facilitated communication between Karen Mager and provided a powerful computer for processing image annotations, and also provided guidance on how to proceed when we encountered obstacles. The core aim of this AI-assisted image annotation application is to provide essential data for the land bridge proposal over the I-5 highway near Ashland. Federal Highway Administration has cited an average collision cost of $17,500 and national annual cost around $8 billion. Oregon is no different and experiences roughly 6,000 deer and elk collisions yearly, totaling $205 million in damages, not including damages from other wildlife such as turkeys and bears. Studies show land bridges can cut vehicle-wildlife collisions by 90% by providing safe animal crossings over and under roads. The construction of this land bridge could decrease collisions and also save about $90 million by reducing the annual cost to $10.5 million for Oregon. Though initially rejected due to budget concerns, the substantial savings and safety benefits has made the land bridge proposal a high priority for future approval. This image highlights the hotspots of vehicle-wildlife collisions in Oregon. The circled area is the planned construction site for the land bridge proposal. What are camera traps? Camera traps are enclosed, motion-activated cameras used to capture wildlife images and videos, often taking thousands of photos. Karen Mager utilizes 11 camera traps in undisclosed locations to gather data for educational purposes and to assist the Oregon Department of Transportation. The camera trap images could support funding by showcasing various protected animals native to the proposed area. It also highlights the activity of elk and deer and identifies potential dangers from lynxes and bears, thereby contributing to our understanding and management of local wildlife. WCAI focuses on using camera trap data to help fund wildlife land bridges. Processing this data involves annotating captured images and videos to identify animals, a challenging task when dealing with partially visible, distant, or camouflaged animals. Karen Mager's growing collection exceeds over 100,000 images. Despite the huge workload of manual annotation, a skilled annotator from SOU can process 1,000 images hourly using time-lapse, an annotation application. With about 1,300 new images each month, the annotation demands only grow, risking inaccuracies and longer completion times due to burnout. WCAI seeks to improve annotation efficiency, aiding in conservation efforts. WCAI accomplishes this by improving image annotation with these key features. Feature 1. Utilize a pre-trained AI model, a tool that identifies patterns and predicts outcomes by being trained on large datasets in order to classify animals, humans, and vehicles in single images. Feature 2. Significantly cut down processing time by processing batches of images simultaneously. Feature 3. Draw bounding boxes for easy visual identification of detected objects. Feature 4. Summarize classification results showing object counts per category. This is available in HTML format for quick data overview. Feature 5. Identify specific animal species, aiding in precise data collection for conservation funding, particularly for these protected species. Feature 6. Analyze videos, applying classifications and bounding boxes to these videos. WCAI employs these tools for image classification, the important ones being Megadetector GitHub repository. Developed by Agent Morris, this resource provides a pre-trained model and detailed guides for image classification using the YOLO 5 algorithm for efficient and accurate object detection. Lambda Altair, a high-performance machine equipped with a powerful 4090 GPU, acquired to enhance WCAI's processing performance, improving speed over CPU-based processing. This is our version 1 demo. You can watch it at your leisure. In order to discuss our results, we need to establish clear definitions. True negative. Outcome where model correctly does not identify object when it is not present. This pizza is correctly not a hot dog. False positive. Outcome where the model incorrectly identifies an object when the object is not present. This dog is incorrectly a hot dog. False negative. Outcome where the model does not identify the object when the object is not present. This delicious hot dog is apparently not a hot dog. True positive. Outcome where the model correctly identifies an object when the object is present. This hot dog is correctly a hot dog. These equations in the bottom measure the effectiveness of WCAI. When WCAI correctly operates on 1,000 images, it achieves 99% accuracy, identifying true positives and true negatives. Has an 81% precision, meaning 81% of images identified are indeed positive, and shows a 93% recall, correctly identifying 93% of all actual positives.
Hello and welcome to testing. So test procedure 1, processing single images. We tested animals, vehicles, humans, no objects, and combinations. We are currently working on weasels, wolves, and bats. Our test procedure 2, processing a batch of images. Currently, we can process 1,000 images in under 2 minutes with Bernie's machine. And from what we learned, roughly 90% of animals detected by a human expert, also detected by a MIG detector in our first folder. Test procedure 3, uploading the results. This is a challenge, because we're working with terabytes of data, and Box and Drive are having issues with that large load. Test procedure 4, are non-detections reliable enough? So 900 out of the 1,000 photos, 965 were non-detections or true negatives. 27 were true positives. 6 were false positives, and 2 were false negatives. So why were these missed? Well, let's look at example 1. Here's our image. It might take a bit, but if you look at the top right, there's something there. That is a bird, and it missed that. But it kind of makes sense why I missed it. It's kind of hard to tell. Let's look at example 2. If you look around, you may see a bush, but it's not a bush. That's a squirrel. And you can kind of see how it'd be easy to miss that as well. I assume that around most of the class will see both animals, as they're not really hard to tell, but they could fool you if you're not paying attention. Let's look at the results. So it only missed 2 out of 35. That is a great percentage to have. It's above 90%. But there's a caveat. It's not great with non-animals or false positives. I went through all 13,000 images to really check this. So, how many false positives? A lot. There's a lot of false positives. So, large falling snow clumps, faraway bushes, small round shadows, and large sticks are the main culprits for why there are false positives. Let's see some examples. Look back there. There are a couple of bushes. And Wakai loves to annotate those bushes. And just that shadow at the bottom right. It loves to annotate that shadow right as well. That shadow at the bottom, kind of an anomaly. That snow, I personally don't know why. And that stick, there's a bird that lands on that quite often, and it might be confusing that for some reason. So let's look at the results. About 50% of the detections are false positives in our main folder of 13,000 images. This is a problem. A very big problem. It ruins the validity of Wakai. So this is a tough problem to solve. Let's look at the division of labor. Eric coded a GUI that helped make it easier to run a program. He helped debug Wakai, the output, helped debug the VPN access, and document Wakai app and VPN access. I worked on system analysis documentation, revisions, and the use of Wakai. I also implemented Wakai on Colab Jupyter Notebook, and I manually checked all the data. Our roles will change next term, as documentation will be required, and more training and coding will be required. In conclusion, Wakai positive impacts proposal for the bridge. Shows which animals may use the bridge, and identifies a protected species. Reduces annotation labor, and allows scientists to refocus their resources elsewhere. We're going to focus on classification integration with video, adding and removing species with Wakai, and reducing false positives. Now that we've covered all that, let's show you how one would use Wildlife Crossing AI with MIG detector. Here we will show single image processing, batch processing, and creating JSONs and how to use them. Welcome to Wildlife Crossing AI. Here we will begin with our Jupyter Notebook called First Time Setup. This is for users who have not used Wakai or MIG detector. So Wakai, or Wildlife Crossing AI, is our version of MIG detector to help the staff and students of SU Wildlife Science Department by using the time it takes for them to annotate images of animals for the land bridge proposal. They have hundreds of thousands of images and videos equating to terabytes of data. We have much information available on each step for the user so they understand what's going on. We have added the Git repos for the users, MIG detector, and LibV5. This shows the user where to download them in case they are not currently on the machine. However, on our machine, they are here, so these are commented out. Let's go to importing a tool. Let's import OS. This is a tool for file pathing. This will help the user know where they are in the system, and much more. Let's do a quick print, show where we are. We're in documents. Let's change the directory. That doesn't exist because that's not after documents, but that's fine. Now let's go to environment. We no longer need to run the environment manually as we've created a kernel that does that for the user. All we need to do is select the Wakai kernel and it should have everything for them. However, we've left everything here just to show the user what it takes to create the environment manually, or in case they want to move this somewhere else and don't have access to Wakai kernel. This has been tested and works. And upon completion, successful completion, we'll return this right here. Wamba activate camera trap slash detector return code 0. And it's just verification right here. Now, image processing. This is the main purpose of Megdetector over Wakai, processing images. To begin, let's look at single image. Here, the user will select a single image they want to annotate. It can be from anywhere. It does not matter where that image is from. Here, I selected Ornkia. I don't know how to say this. Whatever image, and saved it to an image path variable. We save things to variables for the users especially, so they don't have to keep typing this or copy pasting this. It's very troubling. So we'll now run the Python command run_detector.py. We will also include the model. This is important as we have several models. This is the default model that has all the basic classifications. Let's run this. As you can see, it downloaded the model successfully. It ran the detector on the one image. It activated PyTorch, CUDA. It used the GPU, imported the ULV5, and all the good stuff. This is not an error. It looks like an error. We do not know why this is happening. But this is success. So now, the image will have appeared in Megdetector, images, all the way down here. As we can see for our success, it gives us the annotation box, percentage confidence, and what classification it was. In this case, it is animal. Perfect. Let's go back to where we were. Now, we want to do the main purpose of Wakai, mass image annotation and JSON creation. Here, we have to select a folder that contains other folders that contain images. We cannot just select a folder that contains images. That's just how Wakai or Megdetector works. So the user will find that folder that contains the other folders and then put it right here. Saving it to that folder path, again, so they don't have to repeat it. Going down, JSON. Now they want to develop the JSON file by the Python command run detector batch. It will use the model again, folder path, and this time where the users want to send the JSON, this creates the JSON file and you select what name you want it to be named. So let's run that. Luckily the folder we've selected contains few images and runs really fast. Another successful run. Now, let's say they want to annotate all the images. We're going to set the JSON path wherever the JSON was put. We now want to put the output path. This is important because for this large data, we want the users to be able to put those detected folders wherever they wish for better organization. Now let's run our last command. This time, it's the post-process batch results.py. Because the images have already been processed, they haven't been annotated, and that's the easy part, as you saw how fast that was. All the users need is the JSON path, output path, and the folder path. As you can see, It ran successfully. Let's go to the output path. Let's go back to my detector. Nope, my mistake. Detected. And we'll go to detections. As we can see, there's an animal. There's another animal. Go back one. There's a person and an animal. There's an animal, 2 persons, and a vehicle. A person and a vehicle. Just a vehicle. And our non-detections, as there's nothing there. Hope you enjoyed our video on Wakai. Let's move on to one of the new models we have added, or the wolves model. This will only work for wolves. It only detects wolves. We have attempted to completely rework the Mega Detector model to add wolves on top, but that did not work. However, we were able to create this wolf classifier, or at least Eric was, who put in the vast majority of the work on this part. So, for the end results of the wolf model, it had a 97% success rate of detecting wolves. 1 wolf out of 95 was classified as an animal and a person. 2 of them were missed, but 0 of them were incorrectly classified. In the previous models, it had a 63% of true positives, 35 missed or false negatives, and 0 incorrectly classified. As we can see in the bottom right, the classifier shows wolves with a confidence of 85%. That is pretty good for the amount of training that we have put into it.